Jai Hind everyone. This is Naresh Kumar from Ajay Kumar Garg Engineering College, Ghaziabad. Welcome to the class of Optical Communication. Under Unit 4, today topic will be working of photodetector or photodiodes. Basically, we know that photodiodes or photodetector is the first component in the optical receiver. So, this is an important part which is used for conversion of received optical power into the corresponding electrical signal. So, in this lecture, the main topics that we will cover will be introduction to the photodetectors, what is the working principle of photodetectors, different type of photodetectors will also be covered like PN photodetector and APD photodetector. Then we will cover the detector response time and what will be the effect of temperature on the avalanche gain or APD photodetector. Then we can compare different type of photodetectors based upon various parameters and depending upon the material that is used for fabrication of photodiodes or photodetector. Then finally we can calculate the signal to noise ratio with the help of different type of sources, different type of sources of noise or error present in the photodetector or in the optical receiver part. So first of all, introduction to the photodetector. Okay, so photodetector is one of the most essential component in the optical fiber communication system. Basically, photodetector is used on the receiver side. In the optical communication system, on the receiver side, the first component that we require is photodetector. Okay, so photodetector is basically works with the help of reverse bias. As this is a diode, so diode can be either the forward bias or the reverse bias. So the photodetector or photodiodes work in the case of reverse biasing. Then what will be the main use of these photodetectors? Photodetector is basically first component in the optical receiver and the main function of this photodetector is to convert the corresponding received optical power into the electrical. That is, optical to electrical conversion is performed by the photodetector. Okay. Now, what is the most important criterias for performance and compatibility requirements for the detectors? That is, what are the suitable characteristics which must be present in an ideal photodetector or a good photodetector? So, these characteristics or requirements from the photodiode or photodetector have been listed here. These critical requirements for the photodetector are like photodetector should be of small size, size of the photodetector should be as small as possible. Then is suitable material. Photodetector must be made up of suitable material, like it may be made up of silicon, germanium, indium, gallium arsenide, depending upon the requirement. That is, what is the requirement of bandwidth, what is the requirement of bias voltage, what is the requirement of dark current, etc. So depending upon the requirement, like if we have to operate for a short distance, then the material used will be different for the photodetector, and if we have to operate for the long distance communication, then the material used will be different for the photodetector. Next important characteristics for the photodiode or photodetector is high sensitivity. That is, the photodiode or photodetector must be highly sensitive. That is, it must have the capability to detect even the weakest possible optical signal. That is, if we are getting even a very weak strength optical signal, that must be converted into the electrical form. This is the meaning of sensitivity of the photodiode or photodetector. So the photodiode or photodetector must be highly sensitive so that it can detect the weakest possible optical strength signal. Next is fast speed or detector response time. Okay, we know that the photodetector converts the corresponding optical signal into the electrical form. So the speed of photodiode for converting the received optical power into the electrical form is termed as the speed of the photodiode, and it is measured in the response time of the photodiode. So speed should be fast, or the response time of the photodetector should be as minimum as possible. Next is sufficient bandwidth to handle very high data rate. We know that in the optical communication, generally we deal with the very high data rate, let's say 1 Gbps or 10 Gbps, and in some cases even more than 100 Gbps. Okay, so the photodetector must have sufficient bandwidth to handle the high data rate. Next is low cost with high reliability. We know that the cost factor is very important. So the cost of photodiode or photodetector must be as low as possible, and the photodetector must be highly reliable. Then noise. A photodetector must introduce a minimum noise. Okay, the errors or noise produced or generated in the photodetector should be minimum or as low as possible, so that we can have a high value of signal to noise ratio. Examples can be, for example, dark current, surface leakage current, and shunt conductance, etc. These must be as low as possible. Now, based upon these requirements, a number of devices or components can be used for optical to electrical conversion. For example, we can say that the phototransistors, pyroelectric detectors, photomultipliers, so these components can also be used for optical to electrical conversion. However, based upon these requirements like small size, suitable material, high sensitivity, fast speed, and sufficient bandwidth, low cost, minimum noise, etc. Based upon these requirements, these photodetectors gives the best response. That's why instead of phototransistors, pyroelectric detectors, photomultipliers, and among the photodiodes or photodetectors, we prefer this photodetectors in the optical receiver for optical to electrical conversion. Now, the working principle of photodiode or photodetector. We know that photodiodes and photodetectors are used in the receiver side. These work with the reverse biasing, and main function is optical to electrical conversion. So the same working principle is explained here, that can be used for optical to electrical conversion. Okay, so we can see that this is the diode, photodiode or diode. This is P type, this is N type, this is depletion layer, and as we have know that the photodiode or photodetector work with the reverse bias. So reverse biasing is applied, that is, this N is connected with the positive of the battery and this P is connected with the negative of the battery. So when the reverse biasing is applied, before that basically this photodetector is used for optical to electrical conversion. So optical is here as input signal and the corresponding electrical converted signal is act as here as output signal. So the input optical power is incidented over the depletion region. Okay, so whenever an optical signal having energy greater than the band gap. Okay, so whenever a photon having energy greater than the band gap of the material is incidented over the photodiode, it will absorb energy, absorption will be there, and it will go from this lower state to higher state. That is, a pair of electron and hole is created. That is, by the absorption of optical power, free electron and hole pair is created. These electron hole pair generated with the help of optical power are known as photocarriers. Okay, that is, when the energy, optical energy incidented over the photodiode having energy greater than the band gap, this energy is absorbed and a pair of electron hole pair is generated, and this is known as photocarrier. Now, under the condition of reverse biasing, these photocarriers start moving. Under reverse bias, these photocarriers start moving, and due to their motion, a current is generated denoted by IP. This current is known as photocurrent, as this is generated because of photocarriers. So, in this way, by incidenting the optical power over the photodetector, we get the photocarriers, electron and hole pair, and under the influence of reverse bias, they start moving and a current is generated across the load resistance known as the IP or photocurrent. So, in this way, the photodiodes are used for converting the received optical power into the corresponding electrical form. So, same principle will be used into the different type of photodiodes like PIN photodiode and APD photodiode. Next is different types of photodetectors. Photodetector used in the optical communication generally is of two types. One is PIN and second type of photodiode is known as APD, avalanche photodiode and PIN. So, first type is that we are discussing here is PIN photodetector. Okay. So, as clear from the name, the structure of this PIN photodiode will have a P-type layer, a N-type layer and a intrinsic layer, I layer. And as we know that we have studied in the physical principle, this photodiode also work with the reverse biasing. So, this P is connected with negative of the battery and this N is connected with the positive terminal of the battery. And in the I layer, the optical power, received optical power is incidented over the depletion region of the PIN photodetector. So, if this incidented optical power has energy greater than the so this incidented optical power must have the energy greater than the band gap of the I layer, and if this is the case, the absorbed energy will result into the electron and hole, that is photocarriers are generated. So, this will result into photocarrier, and under the influence of reverse biasing, these photocarriers start moving, and due to the motion of these photocarriers, a current or known as photocurrent is produced across this load resistance. That is, optical power P in is incidented over the I layer because of absorption, electron hole pair is generated, and under reverse bias these start moving and these result into the photocurrent IP. So in the photo detector, basically input is optical power and output is photocurrent IP. This is optical and this is electrical. So hence O to E conversion is done with the help of PIN, photodiode or photodetector. We can see that the absorbed optical power decreases exponentially as a function of distance or depth in the material. This is the value of power absorbed by the I layer or intrinsic layer, and this is the corresponding value of photocurrent generated across the load resistance. So this depends upon charge on electron, power of photon h n, P in, that is incidented optical power, 1 minus e raised to power minus alpha w, where w is the distance or width and alpha is the absorption coefficient, and we know that the photo carriers are generated corresponding to the absorbed light only. So here we have taken as the 1 minus reflected light. So corresponding to absorbed optical power we will get the photo carriers, and the corresponding to that we will get the photocurrent IP. Then we can calculate the efficiency for the photodiode or photodetector, denoted by eta. We know that efficiency can be simply the output by input. Okay. So in this case, output is photocarriers generated, electron hole pair, and input is number of incidented photons, because photodiodes convert the optical power into the corresponding electrical signal. Okay. So input will be number of incidented photons and output will be number of electron hole pairs generated. So how we can calculate this? The number of electron hole pair will be total photocurrent generated divided by the charge on the electron. Okay. So the number of electron hole pair will be photocurrent divided by charge on the electron. Then number of incident photons will be total incidented optical power divided by the power corresponding to one photon. So we can get the number of photons. So number of photons we can simply get is incidented optical power divided by the power corresponding to one photon. So this is the efficiency of the photodiode or photodetector. One more parameter that is used to describe the photodetector is responsivity of the photodiode or photodetector. Responsivity is simply the ratio of two parametric values that we obtain at the output to the corresponding input. So we have noted that on the output what we get is photocurrent IP, and on the input what we apply is incidented optical power. So this ratio, denoted by the unit of ampere per watt, this ratio is known as the responsivity R of the photodiode or photodetector. Then simply we can put the value of either IP or P in from this equation. So we can calculate the responsivity in terms of efficiency also. So we can calculate responsivity as eta q by h nu. Okay. So this is simply the responsivity of the photodiode or photodetector. Then next type is avalanche photodiode APD. Okay. Second type of photodiode or photodetector is APD, avalanche photodiode or photodetector. This is also known as photodiode with internal gain. Denoted by M. So, PIN is a photodiode without internal gain, whereas this APD is known as photodiode with internal gain. Okay. So, PIN without gain and APD is with gain. This APD is also sometimes known as RAPD. That is, to achieve this internal gain, we require a spatial structure. This structure is known as the rich through structure, and hence the photodiode is known as the rich through avalanche photodiode or photodetector. Okay, that is, in the case of avalanche photodetector, we get the additional photocarriers which result into the internal gain, and to achieve this internal gain, what we require is a spatial structure known as the rich through structure. That's why this APD is also sometimes known as RAPD. Okay. So, this APD is used, as we know that this provides internal gain. So, this is used for providing the additional performance enhancement, or we can say that the sensitivity of APD is high. Sensitivity of APD is high. Okay. Another requirement for this avalanche photodiode is, we know that the photodiode work with the reverse bias. So, this to achieve this internal gain, we require a comparatively high reverse bias voltage in the case of APD as compared to PIN. So, in this case we use a comparatively higher reverse bias voltage. Okay. This higher value of reverse bias will help us in achieving the avalanche multiplication or getting more and more number of photocarriers, so that the photocurrent generated will be multiplied by the additional internal gain. So, in this case, in the case of APD, what we get is internal gain. This internal gain is achieved with the help of additional photocarriers. Additional photocarriers. These additional photocarriers is also known as the secondary generation of carriers. Okay. What happens is that in this case, by the absorption of photons, we get electron and holes. Electron hole pair is generated, and we know that a high value of comparatively higher value of reverse bias is applied. So, under this very high value of reverse bias, these generated photocarriers gain enough energy so that they ionizes the bound electrons, and their velocity will increase in such a way that they collide with the lattice and they will create further electron hole pair. That is, electron hole pairs are generated by the absorption of photons, and under the reverse bias they gain enough energy so that they collide with the lattice and they further generate more and more electron hole pair. So when first time this carrier multiplication take place or photocarrier multiplication take place, this is known as the impact ionization. The phenomena used is known as impact ionization. Now, under the effect of highly reverse bias, these photocarriers generated with the help of impact ionization, they are further cause the more and more number of photocarriers, and this effect is known as the avalanche effect. So first of all, by the absorption of photons, electron hole pair is generated, and under the influence of reverse bias they gain enough energy that they get further more and more electron hole pair. This is known as impact ionization, and these after impact ionization they further generate more and more photocarriers. This is known as avalanche effect. So this internal gain is achieved in the case of APD using the impact ionization and avalanche effect. Okay, so impact ionization or avalanche effect is the reason for the internal gain in the case of APD. This is what we have discussed. To achieve the internal gain, we have to use a special structure known as rich through. That's why this APD is also known as RAPD. So this is the structure for RAPD. We have a N positive layer, P type layer, P positive layer, then we have a intrinsic layer, I layer or pi, pi means Pi. We have a P type layer with intrinsic layer with slightly doping of P type. Okay, and we know that as compared to PIN, we have to use slightly higher value of reverse biasing. That is, only after achieving a certain value of electric field in the reverse bias, this is the minimum value of field required. Okay, so this avalanche region will be the region where the impact ionization will take place or avalanche effect will take place. So reverse biasing should be there sufficient value of reverse biasing so that we can get the impact ionization or avalanche effect, so that more and more electron hole pair can be generated and corresponding photocurrent will be multiplied by the internal gain M. And this reverse bias should be less than the breakdown. That is, if breakdown will be there, then the carriers will be infinite. So we have to operate below the breakdown. This is what we have discussed. In the case of APD, what we get is internal gain. Internal gain is denoted by M. So M will be equal to IM divided by IP, or we can say that photocurrent obtained in the case of APD will be normal photocurrent corresponding to PIN multiplied by the internal gain. So because of impact ionization or secondary carrier generation, the gain is achieved in the case of APD. That is, in the case of APD, simply we can get the value by multiplying the factor M with that of PIN parameter. So for example, if we have to calculate the responsivity for the case of APD, it is simply the responsivity for the case of PIN multiplied by the M. So we can simply write as m multiply by the responsivity, that is eta q by h nu. So any parameter value we can calculate for the APD corresponding to PIN by simply multiplying with the internal gain m. Next is detector response time. Basically, detector response time gives the speed of the photodiode. Speed of photodiode. The speed of photodiode should be very fast, that is response time should be minimum. Response time should be minimum. So we have to study the factors which are responsible for detector response time, or what are the factors that make the detector response speed slow, and what are the factors which are contributing for making the detector response fast. So this is the diagram for the photodiode, PIN photodetector. This is the width of the depletion region. This is the optical power that is incidented over the eye layer, and reverse biasing is applied there. So when the optical power is incidented over the eye layer, photocarriers are generated, electron and hole. But it is not necessary that optical power will be incidented only over the eye layer. Some power may fall outside this depletion region. So that will also generate the electron and hole. So the phenomena that take place inside this depletion region is drift of carrier, whereas outside the depletion region is diffusion of carriers. So there are two factors which are contributing to the photocarriers or current IP, photocurrent, for the case of speed of photodiode. One is drift, another is diffusion. Drift is under the influence of electric field, so drift is a comparatively fast mechanism, whereas diffusion is a random process and it is comparatively slow. So out of the two processes, drift and diffusion, drift is fast, diffusion is slow. So drift will try to make the detector response or speed of the photodiode as fast, or detector response time as slow, and diffusion will make the process as slow. So but combinedly we have to take the effect of both. So overall detector response will be fast because of drift and slow because of diffusion, and overall response will be slow because of diffusion, as we have to consider both. Next is, we have shown the equivalent circuit of the photodiode receiver. Photodetector receiver is there. So first component is photodiode or photodetector. Then we have a front end amplifier, and this is the equivalent circuit. From this equivalent circuit we can see that there can be a number of resistors and capacitors that are present in the photodetector receiver. So one may be like capacitance may be amplifier capacitance and junction capacitance CD. Resistance may be load resistance RL and amplifier resistance RA. So these combined can be denoted by the CT, and combined resistance can be denoted by RT. So a number of resistance and capacitance are present in the equivalent circuit. So these will make the factor contribute towards RC time constant. Okay. So what are the factors that are contributing to the detector response time? One is drift time of the carriers through the depletion region. We know that drift is fast, so time taken for the drift will be T drift equal to width of the depletion region divided by the velocity of the drift velocity. So it will be low or speed will be fast. Okay, then diffusion will be d square by 2 dc, where this dc is diffusion coefficient and d is the distance. So this diffusion is a comparatively slow process, making the overall speed of the photodetector as slow. Then third factor will be RC time constant. So as we have studied, this RC equal to time constant. Okay, so to make the detector response fast, we should make this capacitance as low as possible. So there can be junction capacitance that may be present in the photodetector. So to make the overall response fast, we need to reduce the value of C as low as possible. So here we can see that the detector response time, this is the optical input pulse, this is the corresponding output pulse. When the value of C is small, the response time is fast. When the C is large, capacitance is large, the response time is comparatively slow. So that's all for this lecture. Thank you.